Hi guys, today I want to talk about intermolecular forces, or IMFs. IMFs are forces of attraction between oppositely charged particles or oppositely charged molecules. And not to say that the molecule itself has full charges on it. We're not necessarily talking about ionic compounds, although we will in this video. We're just talking about slight charges that are coming from things like polarity, if there's an uneven distribution of electrons, etc. So intermolecular forces are what cause molecules to stick together, and they actually use the term stickiness when we're talking about these forces of attraction, which I think is sort of endearing. So we have this kind of stickiness between molecules that happens from opposite charges. And there's a few different types, and the first one I think is kind of the easiest to see. It's called dipole-dipole. We know that a dipole, if we're picturing this on a molecule or on a bond, is a symbol that we use to show that there's a slight positive charge on one side and a slight negative charge on the other side. So for a polar molecule with a net dipole, then it's going to have an uneven enough distribution of electrons to have one side that's slightly negative, one side that's slightly positive. So a dipole-dipole attractive force is between two polar molecules. And they stick together because of that attraction between the opposite charges. So let's take something like HCl. So if we look at an HCl, here's the Lewis dot structure for HCl. Then we know that chlorine is more electronegative than hydrogen. If we look at the differences between them, we know that there's going to be a net dipole on this molecule, where that's kind of showing where all the electrons are wanting to hang out. If we're visualizing the electron cloud around this thing, then there's more of them on the chlorine side, fewer on the hydrogen side, right? There's this uneven distribution. So because of this uneven distribution, there's a slight negative charge over here, a slight positive charge over here. Now this is just one molecule, but if I have a bunch of them, let's put another HCl on here, that has the same dipole, it's the same molecule, the same uneven distribution of the electron cloud with this slight negative here, slight positive here, then there's going to be this attraction between these two molecules, between the slight negative on one and the slight positive on the other. And this force of attraction between these slight partial charges is called a dipole-dipole attraction, and that causes stickiness or attraction between those two molecules. So that's dipole-dipole. It's pretty strong. It's pretty strong, I say, because it's only a partial charge. It really depends on the net dipole. It depends on the magnitude or how unevenly distributed these electrons are as to how sticky they are to each other. There is a stronger version of a dipole-dipole attraction that is called hydrogen bonding. And hydrogen bonding is a specialized dipole-dipole that comes from the hydrogen on a polar molecule. So this is attached to something else here. And that something else is more electronegative than my hydrogen. So the dipole is going to be pointing towards that something else. And then it's going to be an oxygen that's attached to something else, a nitrogen attached to something else, or a fluorine attached to something else that is slightly negative. So it is more electronegative. So the dipoles in all of these cases are pointing in this direction. So there's this attraction then between the slight positive on a hydrogen from one molecule and the slight negative on either an oxygen, a nitrogen, or a fluorine on a second molecule. This is a dipole-dipole attraction still, because we're still talking about polarity with both of these types of molecules, but it's specialized because of the hydrogen piece. And this is the strongest of the intermolecular forces. Strongest of the forces of attraction between molecules. That's what inter means. Intermolecular, between molecules. Now, in recent years, they've also found that sulfur can do this. So in some textbooks, this isn't even listed, but there's also potentially hydrogen bonding that has been classified with sulfur-containing compounds as well. This is a little less common. The The research is a little newer. So usually it's the oxygen, nitrogen, fluorine, the NOF, or if you wanted to add the sulfur in there, SNOF. Those are your hydrogen bonding options. So we see this in things like water, for example. So if we take our water molecules, their little Mickey Mouse lone pairs there, we know that there's a dipole, a net dipole on water, which goes towards the more electronegative oxygen. So there's this slight negative side, slight positive side. If I have another water molecule in here, it has that same net dipole, which is pointing up through the center, right? If I add together the two dipoles, it's going to give me this net dipole towards the center, which shows me where all the electrons want to hang out. They like to be up here by these lone pairs. And so because it's bent and because of the polarity of the bonds, then we have this net dipole on the structure, and there's this force of attraction between the slight negative on one and the slight positive on another. That is hydrogen bonding, and it causes the water molecules to stick together in a very strong way, which causes a lot of the interesting features in water, like surface tension, has high cohesion because of this, which is stickiness to itself. So hydrogen bonding is a very important component of water and water's chemistry and how unique water is, because there's a lot of really cool and interesting things about water, and a lot of it comes from hydrogen bonding. That's usually the answer to all questions when it comes to water, is why does water do that? Usually the answer is hydrogen bonding. Now in terms of the different forces here, the weakest are called van der Waals forces, or London dispersion forces, or dispersion forces. London dispersion isn't named after the place, it's named after a chemist by the name of Fritz London. Van der Waals is the same guy that we talked about if you've seen my video on real gases. There's the van der Waals equation that talks about kind of what factors we have to mess with in the ideal gas law when we're dealing with real gases or gases that have stronger intermolecular forces. Now van der Waals is a force of attraction due to the random distribution of electrons. And van der Waals forces are in everything. It's a rare moment that I would say an all or never in these videos. I usually like to hedge my bets a little bit and not make broad generalizations like this. But because van der Waals forces occur because of this random movement and distribution of electrons, then all things have the potential for van der Waals. Now, you have to be careful when you're looking at this term in biological contexts. Sometimes biologists use van der Waals to talk about both dispersion forces and dipole-dipole attractions. So it depends on the context here, and I tend to not like the term van der Waals. I tend to use dispersion forces when I'm talking about these. So if it's in all things, that means I could have something with no net dipole on it. Let's take diatomic chlorine, for example. In diatomic chlorine, because they're both the same thing, the electronegativity is the same, and we can assume that the electrons are going to be distributed pretty evenly throughout the structure. But because electrons are always in motion, that's kinetic molecular theory, that everything is always in motion, unless we're at absolute zero, in which case we have other problems to deal with. But because of the random movement of electrons, you may at any one given time have a slight pocket of electrons up here and a slight deficiency somewhere else on the molecule. So maybe I have, because of just things randomly moving around, maybe I have kind of a cluster of electrons over here and kind of some evenly distributed throughout, but just they end up kind of clustered together, and in that brief moment then there's going to be this slight negative charge, this partial negative charge. Again, that's a lowercase Greek delta. And then where there's a deficiency, there's going to be a slight positive charge. Well, this is happening all the time in things. And if this guy comes and bumps into this one, the cloud around this guy is going to shift. If we have a bunch of electrons over here, the electrons on this guy are going to shift away. right? They naturally want to repel each other. So they're going to move, even though they're evenly distributed, they're moving all the time. We might have this slight cluster of them down here then, as they're trying to repel from this, which leaves a deficiency here. And now, even though there's no net dipole on either one of these compounds or either one of these molecules, there's still a force of attraction briefly, instantaneously between these two molecules, this stickiness between molecules. So this is short-lived. It's weak. It's actually the weakest of all of the intermolecular forces. And it's in anywhere where we have electrons that are moving around. So it's sort of most interesting in nonpolar compounds or molecules. So in the other examples with dipole-dipole and hydrogen bonding, those are only in polar molecules. We'll only see that in nonmetals with nonmetals that have a net dipole on them. But in these guys, with van der Waals or dispersion forces, we see them in everything. And it's really the only thing that is in nonpolar compounds that allows them to stick together. And so because that's the weakest force, and because these things don't have a lot that's causing them to stick together, then these nonpolar compounds tend to be a little more volatile. They don't stick to each other as well in the liquid phase. And we'll talk in future videos about the characteristics that can evolve from the different intermolecular forces in various liquids. But this is kind of the idea. Random motion of electrons can cause this sort of instantaneous or induced dipole. It's a dipole where there isn't normally a dipole. And it's this really fast, weak attraction that can potentially happen between molecules that don't normally have these poles on them. All right, there's one more that's important when we get into mixtures. So another important intermolecular force is ion-dipole. And as the name implies, ions, of course, are charged atoms, either positive or negative, and dipole is a polar compound. So if we have something like water and sodium chloride, we know that sodium chloride actually will dissolve in water, which means it splits into its component pieces. It splits into sodium ions and chloride ions. And we know that water is polar and has a slight negative charge on one side, a slight positive charge on the other side. So when it dissolves the sodium chloride, the slight negative charge is actually what's going to be interested in my sodium ion here, my cation. So when the water molecules surround this and pull it apart and dissolve it, then there's going to be this attraction between this positively charged ion, my cation here, and the slight negative charges on my oxygens. And then the opposite is going to be true on my chloride. So my chloride ion here is going to be attracted by the slight positive charge from the hydrogens on my water. So when we say that something dissolves, we mean that it's surrounded or split apart by water, or whatever the solvent is. In this case, it's kind of easy to think about in terms of water because of the polarity. So there's this force of attraction between the slight positive charge because of the uneven distribution of electrons on water molecules and the charged atom that is our ion. So this is another intermolecular force that you'll see. It's especially important in solutions when we start to mix things together, and it'll have impacts on the way that characteristics of that solution and how the liquid changes depending on what is dissolved in it. If you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.